In this video, we are going to study impulse signal. To understand impulse signal, we must have knowledge of rectangular signal. So as we know, rectangular signal is given as x of t equal to a rect of small t divided by capital T. Remember here, we are deriving impulse signal, and this impulse signal is derived from rectangular signal. To derive this signal, we need to understand some basic concepts. So this rectangular signal must have area equal to 1. So we will follow step-by-step approach and we will convert this rectangular signal into a impulse signal. So first condition is the area of this rectangular signal should be equal to 1. As we know, area of rectangle is given as length into breadth or width. So here, if I want area of this rectangle to be 1, I need to adjust its width and height in such a way that its area will become 1. So to make this area equal to 1, the value of a and t should be set appropriately. So we will write the equation of this rectangular signal as x of t equal to, now let's say I will assume the width of rectangle as tau. If I assume it to be tau, and if I want area to be 1, I need to have its amplitude as 1 by 2. Therefore, if we find area for this rectangle whose height is 1 by 2 and its width is 2, so we'll get area equal to 1. So with this equation, we can derive the impulse function. So let us draw this signal first. So here we have the time axis t, we have origin, and the y-axis represents the magnitude or the amplitude of signal x of t. And this rectangular signal is represented as, now the total width is 2, so this signal will approach from minus tau by 2 to plus tau by 2. So this will be a rectangular signal with height equal to 1 by 2. Now, to convert this rectangular signal into impulse, we need to reduce the width of this rectangle, keeping area constant to equal to 1. So if I want to keep area of this rectangle constant, and if I decrease the width, its height will increase, so that 1 by tau into tau remains equal to 1. So this can be written as our delta function or the impulse function, which is denoted as delta t, can be derived from this rectangular function by limiting a rectangular signal and making the width of this rectangle equal to 0. Therefore, we need to take this limit as tau tending to 0. So if we decrease the width of rectangle in such a way that its width becomes 0 and height increases accordingly, that signal will result into the impulse function. So if we try to draw such signal, so let's say I will decrease the width of this rectangle, which is tau. So this minus tau by 2 and plus tau by 2 will shift towards the origin, and as it shifts towards the origin, the height of signal is going to increase so as to keep area constant equal to 1. So I will get a signal in this way. So if I decrease it further, its height is going to rise. So for all the cases, area of all the rectangular pulses is equal to 1. So if we go on repeating this process at the condition tau equal to 0, means when width of the signal becomes 0, its height will go to infinity, so that area will be maintained at 1. This is what the ideal condition. So we get impulse function as this will be the axis time. Now y-axis will be denoted with the delta function, which is called as impulse signal. We have origin. Now with this equation, delta t equal to limit tau tends to 0 1 by tau rect of t by tau with tau tending to 0. If we go on reducing this width of rectangle, at the end we get a single vertical line whose width is 0 at origin. So ideally the amplitude of signal rises to infinity when width becomes 0. So this signal is called as impulse signal. Therefore, this impulse function delta t can be now represented as this signal will have amplitude infinity at t equal to 0 and 0 for t not equal to 0, or you may mention it as otherwise. But remember here, this signal will always have area equal to 1. So this equation completes the definition for impulse function. But as we know, practically we cannot have a signal with amplitude equal to infinity. Therefore, we need to derive the next equation called as unit impulse signal. So we have now unit impulse signal. As the name suggests, this unit impulse signal has amplitude equal to 1, and this signal can be denoted as delta t equal to amplitude will be 1 at t equal to 0 and 0 for t not equal to 0, or you can mention it as otherwise. But remember here, this equation is not complete definition for unit impulse. You need to mention its area, which is denoted as integration from minus infinity to plus infinity, delta of, you may take the function as tau, or you may mention it t also, delta t dt is equal to 1. So this completes the definition of impulse function, and it can be drawn as x-axis time, y-axis delta t, and at origin we have a vertical line with arrow and with amplitude equal to 1. So this is the practical notation for unit impulse function. This representation is for continuous time domain called as CT signal. Similarly, we can denote this signal in DT domain also. For DT domain, the equation changes to delta of n equal to 1 for n equal to 0 and 0 for n not equal to 0 and area equal to 1. Similarly, we can draw this signal with x-axis n, y-axis delta of n, and we have a pulse at origin with amplitude equal to 1. So if you look at the representation of signal in CT as well as DT domain, these representations are identical, but remember the properties of this CT and DT are different. So this completes the definition of impulse and unit impulse signal.